Okay, I understand that some of the material having to do with the area under the curve and the relationship between a z-score and that area can be difficult to understand. Let's start out by reviewing what the normal curve represents. Remember, we can think of a normal curve as representing a histogram that looks something like this. The vertical axis in the histogram, as in any histogram, represents the number of values within a particular category of scores, and the horizontal axis represents the scores. Let's think of these as SAT scores. If I remember correctly, the lowest combined SAT score you can possibly get is a 400, and the highest possible score is a 1600. So this bar over here represents people who scored somewhere between 400 and 450. Actually, it's 448, but we're not going to worry about that right now. This bar over here represents people who scored between 500 and 550. The median score is 1,000, since that's halfway between 400 and 1,600, and as you know, all normal distributions are symmetrical, which means that the mean and the median are the same, and that would be this group over here. So the first thing you notice when you look at this distribution is that most of the scores are not that far from the mean, and this is a typical characteristic of all normal distributions. As is the case with every histogram, all the bars taken together show all the possible scores in the sample or a population. Obviously, everybody who took the SAT on this date had a score somewhere between 400 and 1,600. This distribution represents all, or 100% of the scores. Just to restate what I said a little earlier, the largest percentage of scores are closest to the mean. Because the distribution is symmetrical, you know right away that half the scores are going to be less than the mean, and half the scores are going to be greater than the mean. Suppose I told you that this particular bar over here represents people who scored between 700 and 750 on the SAT. If you knew the total number of people who took the SAT, and then you counted up all the people who are in this category, and 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 this category over here, and then divided all the people in this group by the total, you would also know the total number of people who scored greater than 750. So you'd know the percentage of people that scored in here, and then of course you'd also know the percentage of people that scored in here. That's a very simple calculation. At the end of the day, that's all we're really doing when we're looking and messing around with these normal distributions. Let's take this simple histogram and connect the tops of all the bars, and then smooth the whole thing out so that we have this nice looking normal curve. Using what we learned in the last video about how to transform raw scores into z-scores, let's rescale these SAT scores and express them in units of standard deviation. Probably can't quite see these here because they're quite small, so I'll just blow them up for you. Okay, just a side note that out on the tails of the distribution, it is possible to find cases that are beyond 3 standard deviations from the mean, or really any number of standard deviations from the mean, such that the line of the curve, the blue line here, never actually touches the horizontal axis. It's very hard to draw that, however, because the line that represents the curve has to have a certain thickness. If you look really closely, you'll see that the blue line does not, in fact, touch the horizontal axis. But anyway, in the histogram version of this distribution, we could simply count the number of scores above or below a particular score, divide by the total number of scores in order to get the percentage of scores above or below the score of interest. In this version, we can't do that because the line we've drawn is a curve. Because of this, the area underneath is continuously changing. We will still make the assumption that 100% of the scores fall below the curve. But how do we find the numerator in our percentage calculation? How do we find, in other words, the area under the curve? To find the area under the curve, you need either some calculus or a table that gives you the area for any z-score. As you know, 34% of scores will fall between the mean and 1 unit on either side of the mean, 1 unit of standard deviation on either side of the mean. That would be this area over here. Oops. We also know that a little over 47% of the scores would fall between the mean and 2 standard deviations. That's represented by this blue area plus this yellow area here. Finally, we know that nearly but not quite 50% of the scores will fall between the mean and 3 standard deviations out. That area would be this area here, plus this area here, plus this area here. That is a total of about 49.9% to be precise. It should be obvious, of course, that 50% is above the mean and 50% is below the mean. And I'm just going to put that on this side over here to represent it in red. With this information, it's possible to try our hand at some simple problems. Okay, first let's tackle a simple problem. Let's take a look at the percentage of scores that are below 1 unit of standard deviation above the mean. This is the mean, and this is 1 standard deviation unit above the mean. So what we're interested in this problem is we're interested in finding out what percentage of scores are in this region over here. Well, the first thing we know is that 50% of the scores are going to be somewhere in here. Because the normal distribution, again, is symmetrical, we know that half of our scores are going to be in this area over here, the gray. You can see that, the gray arrows. We also know from the text that 34% of the scores, I'll do this in blue, about 34% of the scores are going to be between 1 standard deviation of the mean and the mean. So we have 50% plus 34% equals 84%. So if your score was 1 standard deviation above the mean, you did better on this exam, if it's an exam or an SAT or whatever it is, you did better than 84% of the people in this distribution. All right, let's take a look at another problem. Clean this up again. Now we're interested in finding out the percentage of scores that are above 1 unit of standard deviation above the mean. Above 1 unit of standard deviation above the mean. Again, this is 1 unit of standard deviation above the mean. We're now interested in finding out this area. Well, in the previous example, if we found out that this total area here represented 84% of everybody in the distribution, and we know that the entire distribution is 100%, then we can clearly get this green area over here with simple subtraction. And that's going to yield about 16%. So we can say that 16% of all the scores are above 1 standard deviation from the mean. Let's take a look at another one. What about the percentage of scores that are below negative 2 standard deviations below the mean? This is negative 2 standard deviations below the mean. This is the mean over here. We're interested in finding out the scores in this area. Really the same problem as the one we had just a minute ago. 50% of the scores are in this area over here. 47% of the scores are in this area over here. So we have a total area of 1 minus 50% minus 47%, and that is going to leave us with 3%. This, of course, is the same as this 1 here is, of course, the same as 100%. Okay, so these are some fairly easy problems. I've got a problem for you now which is a good deal more tricky. How about the percentage of scores that are above 1 standard deviation above the mean, but below 2 standard deviations above the mean? That would be this area in here in blue. How would we figure out the percentage of scores that are in this area? Okay. Well, the first thing we know is that this area in here represents 84% of the area under the curve. That is 84%. So what's the leftover area over here? If this is 84%, this area in here is 84%, we have a total of 100%. The area left over in this area here is going to be 16%. So that gives us the blue area plus the yellow, plus the yellow area. However, we're only interested in the blue area. Somehow, we have to figure out how to subtract the yellow area from what we have, from this 16%. All right, how do we do that? Well, we know that the area from 0 to here represents 47%. We know that the area on this side equals another 50%. So that gives us a total area from here to here of 97%. We're only interested in the yellow area, though, over there. So we know that the total curve is 100%. So the area left over here is about 3%. So now we can subtract out this 3% area, and that gives us a remainder here of 16% was here from here to here. So the remaining area is going to be 13%. So these problems can get a little bit trickier. You just have to understand a couple of key things. You have to understand that 50% of the distribution is below the mean, 50% is above the mean. You have to understand that. You have to understand that, of course, this is symmetrical, that the normal distribution is symmetrical. And then you have to understand, and you have to just know what these basic distances are. That is going to be 34% from the mean. This is going to be 47% in total, 40% to the mean, 34% to the mean, and that this area here is going to be, oops, that's to the 3, sorry. That's going to be 49, nearly 50%. Okay. Now let's take a look at a different kind of problem. It's one thing to figure out how to deal with cases where we know what these percentages are from 1 standard deviation, 2 standard deviations, 3 standard deviations. What happens when we have fractional distances from the mean? What if we want to know what percentage is, say, below 0.5 standard deviations, or is above 1.4 standard deviations, like this one here. How do we do that? Well, we have to use either a distribution calculator or a distribution table. First, we'll go over how to use the calculator, and that'll be in the next video.